Thank you very much. Well, it's certainly exciting times, and all the people here in this audience know firsthand what's happened over 25 years with our research and our students and so on. In fact, what we can assume now in terms of the amount of computation and memory, the data and connectivity is awesome, unexpected when I put myself in my graduate student shoes. And in particular, I think the learning and reasoning prowess, the algorithms we've developed over the years, some are old and retooled, others are novel, are leading to new opportunities and directions. I'd like to start with this picture of a graphical model that I worked on as a graduate student. I was plunk in the center of a department at Stanford that was, you might say, ground zero for logic-based reasoning methods applied to real-world problems like production rule systems, where just at the time when I was starting my dissertation work, there was a lot of disappointment in the failure of these logic-based systems to grapple with the complexity of the open world. And I came into Stanford thinking, boy, you know, probabilistic reasoning and uncertainty must be central in cognition, in the way the human mind works, and must be foundational in generating a computational model of intelligence. And I was very excited to work with a team, and it was spanning a couple different campuses at the time, to develop probabilistic models. And this particular model here was designed to capture the expertise of an intensive care unit physician about the problems that might be encountered in ICU medicine, where those nodes are random variables that you typically can observe, especially at the top part of this graph. At the bottom are some observables, and these arcs represent probabilistic dependencies. And we sat with an expert for a week to build this graph, and sat with him probably for another week to basically put probability distributions at every single end of every single arc there. Now, what was exciting in these days was we were developing algorithms that would let you take any subset of findings here that you could see, like blood pressure or heart rate of a patient, CO2 input and output and so on, and reason about the likelihood that this patient was suffering from a pulmonary embolism, or was maybe a kink tube in the ventilator machine, telling us all the probabilities that we couldn't see directly. And this was a marvelous artifact, and the algorithms were beautiful. And this graphical models area is one type of representation that really extended our abilities to represent insight and knowledge. Now, over the last 25 years, we've developed methods to learn these kinds of models and other kinds of models directly from data. And one form of machine learning for building graphical models basically searches through a tree of possibilities of all possible structures generated typically heuristically, because it's an intractable problem typically to generate all those structures, and applies a score, the kind of score you might give to a distinction in the world, like a patient being ill, to each model being the correct explanation for the data, finding the best one, and that one becomes the model that's used for diagnosis, typically in real time. The model that's indicated to be the best, and so on. Now, what's exciting is that this area has been active, and sometimes, for example, you can go from just probabilistic association to causality, and use methods that will tell you the likelihood that an arc is a causal arc. Of course, in a causal situation, like in healthcare, where some factor, like a patient's behavior, increases the risk, we can actually do interventions on the world and change outcomes. So it's a very exciting area that we've been investigating more lately. Now, a very important notion that I don't think is stressed enough with all the enthusiasm about machine learning is that we need to typically go beyond just predictions in the world to actions. And the idea basically is we want to consider a pipeline of data to predictive models that give us probability distributions about things we care about, to actions in the world, to decisions that have high expected value. This is not just about a feed-forward flow here. It's also, when you have a decision model and a decision context, it tells you a lot about the nature of the model you need, the tolerances you have, and also if you need to get more data, for example, in situations where more data will give you a better predictive model, active learning methods take advantage of the decision structure to focus attention on the data that you need to extend those models ideally, especially when you pay for those data points in time or dollars. So I want to just mention a few exciting directions, just briefly, to frame a couple of deep dives I'll do with you in three areas. I'm very excited about causality, as I mentioned, and active learning, which I referred to just now. I think those are very exciting areas. Lots going on in those spaces, and lots more to be done. Another area that's received less attention is the notion of lifelong learning, where I build a system or artifact and have it sit in the world for a prolonged period of time, for example, accompanying the lifespan of a human being, and having it understand what it means to learn over time where context might be shifting or oscillating, for example. And it's not just empirical studies and experiments. There's some deep principles about lifelong learning. What gets thrown out, what gets discarded, what gets brought in real time. Then there are new kinds of methods being developed, quite different but related to the graphical models I talked about, one of which is called deep learning. And with deep learning, the idea is we have a stacked representation. Particular one approach is with using essentially the same neural net technology that was used 10 to 15 years ago. And the idea basically is we can either induce variables or in an unsupervised manner, or in a supervised manner with labeled data, build these models. With large amounts of data, the recent interest and energy has been on systems. How can we actually scale up and through assumptions of modularity of various kinds and approximations to these big search spaces to understand how to share out the effort across large numbers of CPUs. It's a very active area. I have to say that this area a couple of years ago was pioneered as a collaboration between Toronto and MSR Redmond in its application to speech recognition. And the kinds of accuracies seen were big jumps and discontinuities from the best methods of the time applied before this technique was looked at carefully with large amounts of computation and data now available. I should say that you might say that the demonstration that some of you saw yesterday by Rick Rashid on speech-to-speech was in part enabled by this recent jump. You see basically from 1993 to 2011, we had an initial drop on looking at a conversational recognition task called switchboard data, which is the same data essentially we trained the system you saw yesterday for people at the 21st century meeting. But for about 15 years or so, we've been on a plateau until we recently see this change. And it looks like all indications show that if we keep on going, we're going to see continuing word error rate decreases over time. And we're not sure exactly where that's going to go. But you see where the human error transcription rate is. And few people I've spoken to who know this area doubt we're going to hit that eventually, which would be very impressive. Now, another exciting direction is the idea of we have new forms of data. I'll call these ambient or in-stream data resources. Let me give you an example of one set we worked with as a collaboration with colleagues at MIT. And we got access about 2 years ago to all of the cell phone communications data, just counts of calls at cell towers from a 6-day period in Rwanda where an earthquake happened at day 3 outside of Rwanda in Congo. And just by looking at 140 cell towers and the surge of calls over time that happened in each cell tower, we were able to, with some interesting learning techniques combined with expectation maximization, figure out where the epicenter was. A few miles outside the epicenter, just a few kilometers, just from watching the cell phone towers over time. And we can turn that around with a little bit of decision analysis, decision theory, to compute by looking at continuing disruptive areas, where we should look and do reconnaissance under uncertainty, all from this ambient data. So the other interesting thing in our world is that this machine learning and reasoning technology is now behind the scenes in daily life. On the desktop, in the car, in the living room. People using Windows 7 might be surprised if they don't know about this, to learn that the system is learning about them as they work with applications over time. And this is also refined in Windows 8 and in Surface, called Windows Superfetch. And the idea is over time, by time of day and day of week, the system is learning about your actions, and it's learning to prefetch applications into memory before you touch and ask for them, so you have a faster response time. In the car, at least in North America right now, every few minutes in 72 cities, we have models that are providing predictions about the flows on every single surface street, mostly those that are not sensed by any sensor at all, through a generalization process we developed. And these are being used in Bing traffic. And this is default on Windows phones. The way these models are built is we take a bunch of GPS data. In this case, we started with Seattle for about 1 million kilometers, 100,000 trips taken. And we weave together models. We weave together the GPS data with highway data to build models that predict how traffic is going to flow. You need to really understand how traffic is flowing on every single street, typically, to really do a great route plan. A-star or Dijkstra combinations that are used in practice. This shows a path from my home in Kirkland to a place across the lake in Seattle. And as people from Seattle know, the big question is, which bridge do I take, or do I go around the top to Seattle? And it's saying here in this case that it's a 15-mile route. 24 minutes is the best route if you didn't use our predictive models, but the predictive models are telling you to basically it'll take about 50 minutes in current conditions, and therefore if you take the traffic-sensitive approach, you'll go over the top, and that's basically 13.1 miles. It's longer typically, but it's faster. Now, going into the living room, about 10 years ago, our team started playing with a strange thing called the depth camera. This is Andy Wilson here, an HCI person, who realized there was some power to the idea of using a depth camera. Now, going from this kind of playful research, playing with a ball by sticking your hands into the screen with a depth camera, to an actual product is an interesting path, and it's a cross-laboratory story that really leverages machine learning in a deep way. At the time, the obvious way to go from a depth object to an actual motion or a skeleton for tracking for games purposes was by matching to a kinematic model. And it turns out that our lab in Cambridge was doing some long-term research on how do you take videos and segment them, and pictures, and segment them and then do object recognition and tagging. For example, take this picture up here. How do you go from this street scene and have automatic systems that learn to assign pixels to parts of the world that are semantically relevant to human beings? And just at the right moment, this challenge problem landed in the hands of Antonio and Jamie and so on, and they basically did the same thing. It's not like a sheep and grass now, but this is pixel part of a shoulder or a chest or right elbow, and then this method is used to actually create the robustness that's required in that product. So I wanted to basically now, that's some of that background, some things that are exciting, some what's happening in the world now, in living rooms, in the cars, and on our desktops and laps. Focus on several directions that I think will be interesting to this group. First, I'll focus on some work in healthcare. I'll do a deep dive in healthcare and talk about some work there. Next, I'll talk about two thematic, I call them visionary goals, that excite me, really light my passions, and I'm hoping that these will be indications of a path that we're on in each of these spaces. First, in healthcare, obviously the big story about healthcare is that we've dropped so much data on the floor, and we continue to do so across the world in healthcare, clinical healthcare. Amidst the genomic explosion, which is very promising, we're still losing a lot about the behavioral aspects of health, the way healthcare is delivered, and a lot about outcomes. About 5 years ago, we started looking at a particular challenge called readmissions challenge. Patients that are discharged from a hospital bounce back within a month to the same hospital, typically, with the same problem. And the question was, could we address this challenge with these methods? And we had just come into ownership and shared ownership of a large data set of the form that we had never seen before, especially putting myself in my graduate student shoes, of, for example, 10 years of emergency department data. Really rich, 300,000 visits to the emergency department, and everything you can imagine about the patient care and situation, diagnostic codes, medications, vital signs, laboratory results, fees and billing information, even the MD codes. Who are the MDs that engage with this patient? So we looked at about 25,000 variables and started just building models with that graphical search methodology I mentioned. For example, a model that can predict a patient in the emergency department, ED-A, will be admitted, bounce back and be admitted as an inpatient in 30 days to the hospital. And of course, when you build these models, just for people that don't work in this space, what you do typically is and there's lots of variants of this and lots of procedures for refining this, but basically you take a training set, which is usually most of your data, and then you hold out a test set, and that test set is usually the most recent set, and that's going to be a set of patients, for example, that is most like the patients you next see in the world. And then you run your model that you've trained with the test set, and you see how well it does in terms of a true positive rate and a false positive rate. And this ROC curve, as it's called, receiver operator characteristic curve, gives you a sense for how different operating thresholds will work in a hospital. For example, I want to operate my classifier such that I'll capture 76% of the patients and I realize that if I do that, I'll have a false positive rate of 26%. So that's an ROC curve. We typically try to get the area under the curve as much towards 1 as possible. We also learn about what are some important features that the system is discovering. For example, the idea that a patient staying in the ER for 14 hours or more is a bad sign for them staying out of the hospital. We all know that heart failure is a particular challenge, but the fact that English sentence saying dialysis anywhere in the document is a bad sign for staying away from the hospital. We took this work and we're working with the healthcare unit at Microsoft, now Paradigm, a joint partnership with GE, built a system called Readmissions Manager, and this brought up several more issues with tractability, where we were told by the delivery team, it's kind of slow we can't do 1,000 variables. Can you back off? And so we have to use methods that will go search through spaces and will introduce constraints. What if we we can use 50 features or 100 features? What observations you can make about each patient? What's the optimal you can do? And after a while, you make a trade, like we'll go with 66 features, and here's the ROC trade for that value. And the fielded product will basically present for every patient being ready to be discharged a likelihood, and this is sorted by likelihood of being readmitted to the hospital. Once we fielded this, the jury is still out. Can hospitals run this thing locally without experts? What about the data differences and definitions of variables? Do we need a universal schema? We actually get an ROC curve in every new install at Microsoft Research to get a sense for what's going on with that system. And then there's the interesting question, what could we do if we had access to data across hospitals? Could we do better? And it turns out that you often can. Now, I mentioned we built a whole bunch of different models right now. I'm just going to focus on a couple of them I think are interesting. One is a new kind of model we call surprise model. With surprise modeling, we've done a lot of work in surprise modeling, including traffic surprises, and in this case, this is a clinical surprise model. We actually build a database of human surprises, and we train and test off that. So in this case, we capture patients who are discharged and bounce back within 3 days to the emergency department with a diagnosis that was nowhere on their chart. Now imagine being a physician in the ED, and you're told, when this model does its inference at discharge time for a patient, oh, by the way, this patient has a high probability, 0.92 on a 0 to 1 scale, of bouncing back to the hospital in 3 days with a diagnosis that's nowhere on the chart. Do you want to take a peek? You'd think that since we're reasoning now about at the borders of the physician's knowledge, we're not going to be in a situation typically where we're telling the physician what they already know. So we call this a surprise model. And it's these are fun models to build because they reason directly about the stuff people are not very good at catching. One area is that needs, I think, is a real opportunity area for doing new work in machine learning is combining a rich history of time series data with the deep knowledge we have these days of how to do atemporal machine learning. And we've been looking at the challenge problem of hospital-associated infection. It turns out that 1 in 20 hospital visits, probably in the world, but in the US for sure, lead to a hospital-associated infection, $20 billion a year cost. Believe it or not, it's in the top 10 causes of death for any cause in the United States. This is an ROC curve for one of a common infection called C. difficile. Well, it turns out that, and this will be a NIPS paper coming up this December, which we'll have on our site a little bit earlier than the conference. We thought to ourselves, and this is a collaboration with an intern that I continue to work with, who's at MIT, Jenna Weens. If you look at susceptibility and exposure over time in a hospital, they must influence infection rates, these two variables. But these susceptibilities and exposures are time indexed. They change during the course of a hospital visit. Surely they do. And we actually, and the basic idea here is that imagine that a patient comes in and gets seen in different places in a hospital, gets imaged, goes to the OR and back and so on, ends up in an intensive care unit for recovery. So there's a path to a hospital, and we now have the data to look at this over time. We have the lens on the resolution to see this. By pushing this time space with new methods, we ended up going from a 0.69 area under the curve to a 0.8. And what goes on here is an example is that at any location in a hospital, we have the ability now to compute what we call the colonization pressure. In that wing of the hospital, how much of this infection was around. We know all the patients and their diagnoses. So here's a particular patient here, anonymized over time, and they go through a hospital on a visit, and we can go through and over time look at the spikes in infection of certain types across this time range in different wings of the hospital, 2C, 4E, 4F, and understand these rooms. And we can build models that weave together in a time-indexed way, hundreds of variables to come up with better predictors now that take into consideration the structure of exposure and changing susceptibility over time. It's a very interesting opportunity area for us to look at, given the boost we saw in going to time. And finally, I mentioned that there's a really interesting challenge problem in all areas where we apply machine learning, except the simplest areas, simplest perceptual areas, which is action in the world. When doctors see that probability coming up, we've often heard, but we've gotten feedback from our customers. What does that mean? What do I do? And we say, well, that's a risk score. Think about this patient more deeply. Well, it turns out that in many areas of medicine, there's a bunch of work on different kinds of interventions that might be done. For example, how do you minimize readmissions? You might have a post-discharge home-based visit program. You might have a Wi-Fi scale patients can stand on that tracks their weight over time or their compliance with drugs. You might have an education program. All these programs cost money. And the idea is if we know about the cost-benefit ratios, we can build a decision model and come up with a decision threshold and guidance about what to do about those numbers. So we have a study underway right now in Washington, D.C. on congestive heart failure, right in the middle of this work. Now, I just heard that in China, there are 100 million people now over the age 65. This was on CCTV this week while I was in the exercise machine watching television. I was stunned by the number of how many elders there are in China that undoubtedly, many of whom suffer from congestive heart failure. About 6 to 10% of people over 65 wrestle with heart failure. It's a problem that puts patients on edge. They're sort of stable, but outside of the hospital, but they can easily crash into the emergency department, requiring an intensive regime, often referred to by clinicians as a tuning up, which takes about 2 weeks. And there are multiple interventions that have been posed for this at different kinds of dollar values. So to really build a decision model, we had to go to a database at the hospital, and we had to basically figure out what does it cost. Forget about, for now, just health quality, and talk about what it costs for the care. About $18,000 when a patient bounces back to the hospital. They stay about 8.5 days. And we can use these numbers to actually build a decision model and compute a decision threshold. At what probability, given a cost of intervention, should we be paying for that intervention on this particular patient? And the fun thing for us is we have this whole world in machine learning where we take predictive models and we do test and train. I should say train and test to make it more sequential. In this case, we can say train and test, but now on the test set, watch what happened to these patients and actually do an intervention if the system tells us to, and reduce the probability by what the system tells us it will be reduced by the study, and run a whole train and test set with a decision model, rastering over each patient, making a decision for each patient. Yes, extra care, interventions, no, let them go without that. There's often uncertainty before you do a program in how much an intervention costs and how much it'll affect readmission. And the idea is we can actually run that now and compute, and I really like this idea, what is the expected value of putting this decision system in a hospital if you believed that the intervention will cost $400 and reduce the readmissions rate by 30%. And we can compute that in advance. So we have actual dollar values, and these are also aligned with health in this case, about what the expected value of the system operating over time will likely be. So I wanted to just now go from a domain and just give you a sense for an intensive domain we're working with, giving you a sense for some of the newer methods we're playing with, and the frustrations of doctors who get numbers, for example, and trying to come up with a decision plan, to two visionary areas. Now, the first one I'm going to talk about is complementary computing. This is the idea of a vision of humans and computers working together with a much deeper symbiosis. In the spirit of J.C.R. Licklider, who is often an unsung hero of many of the ways we work now with computers, the internet itself. J.C.R. Licklider was a visionary in the 50s and 60s, when he was very active, who really thought deeply about collaboration, connectivity. He dreamed of the internet early on, and he's talking now, or he's talking back then about things that have not yet been implemented, like new kinds of symbiosis. So as one example, imagine someday a human being is faced with a problem here, this blue blob. And imagine a smart computer that looks at that problem with all its perception and reasoning and background knowledge and says, you know, I can decompose that problem into alpha and beta. And by the way, I'm going to communicate that to you, that I've done that. And I'm going to claim that I can do beta better and help you out, but I want to leave alpha to you as the human being. And then this cycles around in an intensely close, connected, collaborative way, potentially with new kinds of visual representations. Well, machine learning and inference are going to play a really critical role in this kind of symbiosis. No doubt. How can this be done? It's an important area, and one that we've been investigating, and one that I've been very passionate about. Let me say that we've done several projects in this space where data, learning, and decision-making becomes core in how machines and humans work together very quickly, typically where the machine can complement the human problem-solving in a valuable way. We've had applications in conversational systems, in systems that do translation. I'm going to talk right now about a recent study we did in citizen science that was published at AMOS this year, and you can read the details online, that actually uses decision theory and machine learning to help citizen science efforts along. Now, citizen science is an area of crowdsourcing, or human computation, which is a rising area. I see many nodding heads. People are following this, where people, often volunteers, will help scientists to tag data, for example, or classify or discover new things with their own volunteer effort. So, for example, we were working with the Galaxy Zoo team based at Oxford and Chicago, Galaxy Zoo is one of the biggest crowdsourcing efforts in astronomy, for example. There's a Sloan Digital Sky Survey which found 1 million galaxies, too many for experts to look at, 120,000 quasars, 250,000 stars. And if you volunteer, you get to look at an image after you get trained up and of a galaxy or a star, and you get to give your vote for what you think you're seeing. And there's after a certain set of votes are received, a label is given as ground truth. This is what we think this is, and thank you for the citizens for helping us label an unlabeled galaxy that has never been seen before by human eyes, given how big the data set is. So the volunteer database that's been built is almost 1 million galaxies, 34 million votes, involving 100,000 people, students, some amateur astronomers, and so on. Now, with the crowd-synth system, we were exploring how can we apply machine learning to enhance this task, to learn from both machine vision and votes. So we discovered that the Sloan survey people had applied a vision algorithm to each of those objects. Now, vision algorithms are tireless. They don't care if it's 1 million galaxies. They can go through and go zip and provide probability distributions over what they're seeing from a whole bunch of features. People are scarce resources. So we thought deeply about if we have machine vision looking at every one of those galaxies, and we have human voters, how do we weave them together in an ideal way? And this is an example of many tasks where a weave is possible. And here come the actual challenges, and we want to use machine learning to figure all that out. Well, it turns out we can learn from a portion of the database how to do ideal fusion of both the machine perception and the human effort to do ideal routing and stopping rules to know when we don't need any more votes, for example, on a galaxy. Here's some of the astronomical features and how they're defined by the vision people working with the astronomers, and that's one of 400 features. The idea is to build a unified model that actually reasons jointly about the implications of machine-identified perception and human votes. It also predicts the next vote any particular individual will give to a particular task, and at all times, what's the max likelihood of what this object is. Once you do that, it turns out you can do routing. And the other kind of fun thing was we could actually look at this big database of people and combine experience with the computer vision features and current activity, like right now, how long have they been on, what's the dwell time between their problems, to route tasks. So we can actually find people who are most qualified at any time to be looking at a particular galaxy. As well as, if someone's not doing very well, we can actually set up an educational system that says, check these two things out. These are different. Do you see that? And make them better at what they're doing. Now, I'm not going to go into details here, but I just want to say, we do, in these detailed studies we do, we can basically, for 23% of the votes, get 95% of the full accuracy of the system, and for 40% of the votes, we can go all the way, and therefore we're saving enormous amounts of human effort here by using this machine learning and decision theory to route tasks to people. Now I'm going to end with the last challenge area I call integrative intelligence. I saw yesterday at the 21st century talks and the questions we heard, lots of interest among young Chinese students. What's the prospect for deeper AI, human-level intelligence? Concerns with or optimistic / pessimistic concerns with robots taking over the world. We had heard a couple of questions on that yesterday. We believe that there's a lot to be done in the space of delivering on deeper experiences of the kind you'd have working with a human collaborator. And one of the approaches, we call it intelligence via composition, where we leverage a tapestry of components, look at the synergies and dependencies among these components, and we ask the question, might the whole we build be somehow more than the sum of the parts? And the comment here, the side comment here, is that back when AAAI, the Association for the Advancement of AI, was a young conference in the 80s, there was sort of one main machine intelligence conference that everyone went to. Whether you did vision or speech, learning, planning. You were at one conference. But with the maturation of the field, by the time I became president, I said in my charter, well, I would nurture the independence, but I also would seek synergies and seek to bring back, to counter the centripetal force of these separate maturing fields. So, CVPR conferences are full of vision people. The conference itself is as big as the main AAAI conference now, if not bigger. ACL conference, for example, NAACL, all the robotics conferences, ICML and speech, KR and inference. Is it possible that there have been maturing advances of the kind we saw in speech, jumps that might change error rates, that when you bring these pieces together might give you new holes because people aren't thinking in an integrative manner lately? And we think the answer to that is a strong yes. And our team, and I think Andrew Eng is here with the Stare Robot effort, very similar efforts to sort of, can we bring these things together in new ways? So the project that we have as our primary project in the space we call situated interaction. And we say that someday, computers will understand in that, let's expand from that small diagram I made that showed the alpha and the beta to alpha 1 to alpha sub n and beta and so on. Lots of sub-problems, lots of coordination going on, let's say in a surgical setting. Or even a smart billboard where a system recognizes there are two people and understands someone has a Starbucks drink in their hand. Or you're in a kitchen scenario and a robotic system says, now, okay, pour that slowly. Okay, now get the sugar, by watching and tracking the situation. And I love this picture because I think that it's quite possible that we will have grandchildren that will be going out for an event, the movies at night, and will be quite comfortable leaving their kids at home with the family robot. And you might tell the robot, call me if there's trouble. Let me know if there's trouble. And you're very confident that the robot will provide a great experience, education, and the kids will have even a better time alone than when you're all hanging out together as a boring family. So as part of this work, we started looking at some social computation. What is it that a receptionist does? By the way, welcome to our lobby at Building 99, Microsoft Research in Redmond. Here's the view out from the reception area. Here's the receptionist, and people here are coming to ask for tasks of various kinds. And with proper disclosure signs up and so on, we recorded about a week of data to get a sense for what is it that the intelligent receptionist does with people. And it turns out it's quite interesting. It's a multi-party experience where someone's asking for a shuttle, and someone else is coming in and waiting, and the receptionist might say, what can I do for you? While the first person is waiting, are the two of you together, and so on. Who else needs a shuttle? And we started thinking about representations, graphical representations of the social situation in terms of how people are engaging, connected, disengaging, waiting, rehydrating. And it's the things we assume are just normal, casual queuing and collaborating in simple ways are very rich challenges to represent computationally. And we built some hardware with some software. This is the schematic view of that colorful chart where I had components up, speech and vision, and so now we're showing you more of a schematic view you buy at the electronics shop. And by putting this together, we could sort of start thinking about what it would be like to build an automated receptionist. I know some of you have seen this because we filmed this about 2 years ago, but it's always good to get a refresher. I'll show a little segment of this for people that haven't seen this before, just a little piece. This red dot here is where the avatar here is looking. And you'll see there's also a notion of pose, where the system thinks people are looking. Notice also the outfits, what people are wearing, formal, casual. You'll see in a second why that's important, but in general, the system uses that information to make sense of things. So I'll show you how that works.
Do you need a shuttle?
Yes.
Which building are you going to? I forget, where are we going?
I think it's building 9.
You sure?
Yes.
So, you're going to 9, right?
Yes.
And this is for both of you, right?
Yes.
I'm making a shuttle reservation for building 9 for
So
2
who has the
people.
slides?
In case you want to correct anything, say or press star over.
So,
Okay.
Are you visiting someone?
Okay,
Yes.
So I think
I'll
everything should
help
be
you
all set.
register in just a moment.
fabulous.
Okay.
So I'll stop there, but there's a longer segment there which shows all sorts of interactions where somebody waiting, the system actually, when that person came in, nodded, like pointed their head towards the person and said, and nodded and said, I see you, hang on a second, let me finish up, and recognizing the attentional status of the first 2 people, turned to one another, and this was a nice time to take a break and address that other person courteously, looking at the formal clothing as a sign that the person was visiting, because no one possibly dresses that way at Microsoft unless they're visiting somebody. The work has continued with fast-paced work looking at, for example, trivia game scenarios, requiring new representations to control the timing of the give and take. Let me show you a little experiment here with people that came in off the street to help us of a question game.
Next question. Libya is the only country with a one-color flag. What color is it?
Let's say green.
Do you think the same?
Yes.
That's right. So far you have 1 correct answer. Now on to the next question. In the USA, hospitals have a Red Cross. What sign do they use in the Arab world?
What's that, a Red Cross? What's that they use in the Arab world?
Solid blue circle.
Is that correct?
No.
So what's the correct answer?
Red crescent moon.
Yes.
That's right.
So what happened there is when that last young lady said Red Crescent Moon, the agent just turned to the guy and raised her eyebrow. And just with the gesture, he was on and trying to confirm someone else's answer. It's a collaborative engagement in this case. Now, we took the best of breed of what we had, which is the blue box here, multi-party engagement and dialogue, and said, can we create an actual daily usable system by my door as an administrative assistant? And we actually added to this core functionality other projects. Now, each of these boxes represents several years of work and publications. Predicting the cost of interrupting me as a worker. Predicting where I'll be next and how long it'll take me to get there. Whether I'll go to a meeting or not. Whether I'll forget something. What's the message urgency, voicemail or email coming in. And gave the system new perceptual abilities. Face ID, room acoustical analysis. Is there conversation occurring, for example? Voicemail, email inputs, calendar location. And this is what I see when I come to work in the morning.
Hi Eric. No one has stopped by to see you since we last talked. And Outlook Mobile Manager is still down, so I'm not seeing messages from your email. Catch you later. Bye-bye.
So inside that system, it's continuing to run cost of interruption. It's computing where I'll be next. If I start a conversation, it computes how long until I finish the conversation in my office for impromptu meetings, for example. Using work that we published at UAI in 2004. And let me just do a couple of vignettes really quick to show you how the system works so you get a sense for it.
Hi.
Are you here?
Oops, hang on a second. This will help you better understand that. So we have had this living by my door for a year and a half.
GMTK thing again?
Oh,
I forget.
Jeff and G-Dub.
Okay. Oh, is Eric? He's not around.
Are you looking for Eric?
Yes.
Are you Dan and Paul?
Yes.
I'm his virtual admin.
Okay.
I know he has a meeting scheduled with you, but he's late from his previous meeting in Building 34. He's no longer on his laptop, so I expect he'll be back in 10 minutes or so.
Okay.
You can go ahead and wait in his office if you'd like.
Oh, we'll come back in a minute.
Okay. I'll make sure to let him know when he returns.
All right, thanks.
See you soon.
So this is Jeff, right? that did
Jeff
that?
Bill.
Okay.
Hello,
Hi.
are you here looking for Eric?
Yes.
Eric is having an impromptu chat right now, but I expect it should be over in around 10 minutes. Would you like to wait for a bit?
Sure.
Sounds good. He shouldn't be too long. Guess I'll see you later then. Bye-bye.
So this system's been up and running, and I have to show you this one segment which happened impromptu 2 weeks ago when an intern on her day before her last day at Microsoft wanted to come visit with me. A little bit humble and timid. I'm not sure why exactly, but she came by and I saw her hovering while I was in another conversation, and she actually engaged with the system. And watch her reaction to first time out of the blue seeing this crazy thing by my door and how she works with it. There was actually another student who had come sitting in front of her that she's engaging with a bit too. But it's fun to watch to get a sense for the future, I think. Hang on. Here we go.
Hi.
Hi.
Are you here looking for Eric?
Yep. Yes.
Eric is talking with someone.
I can
and
see
this
that.
might take a while.
Oh.
But I don't think he'd mind a brief interruption right now. Would you like to go now?
It said so.
Okay. You could check back in 15 minutes or so, and we could see if he's available then.
Okay.
Another option, we could set up an appointment. Would you like me to check his calendar to see if he has any free time later today?
Yes.
All right. No, his calendar shows that he's fully booked today. I'm not sure, but I don't think he'll be attending the meeting on his calendar today at 1:30 p.m. I could pencil
That's
you
like
then.
now.
Would that work for you?
Sure.
Great. Would
Great.
you like me to write this on his calendar?
No.
Okay. Feel free to stop by at that time, but I'm not
Wow.
certain he'll be
This is
here.
amazing.
Yes, I'll see you later then. Bye.
Nice meeting you.
So she actually ended up with a relationship with the robot in a little bit of time there. The same platform has been fielded at Microsoft Research, and we've had it on. We're just doing testing and training and testing right now, which says the elevators are robots, and we should be able to track people's intentions and compute whether they want to use the elevator or not. And if so, elevator doors should be rather like the doors on the bridge of the Enterprise in Star Trek. They should just open for you as you walk to them. It's kind of a magical experience when we've been testing this. Even the elevator problem brings up really interesting challenges. So look what the machine learning algorithm has told us using optical flow features about where the interestingness is. It's not in front of the elevator, it's to the sides. These are where the positive weights are. And turning this over right now, where the negative weights are, where the system has learned to where to look perceptually to figure out is somebody, per their track, per their flow, going to use the elevator or not. And we think that these technologies will not only, in the future, be in front of you as explicit intelligences, they'll not only be collaborative, working side by side in very explicit ways, that alpha and beta, and working with you on getting your tasks done, extending your abilities. They'll also be, like as in Windows 7, few of you knew that there's machine learning and decision-making in that system, in the memory manager. But our grandchildren will expect elevators to not have to have legs jammed in them to open doors. They'll expect the intelligence to be in our environment in deep ways that won't even stand out as interesting. It'll just be the way things are. So I'll just say that applications of sensing, learning, and reasoning are still in their infancy. Infancy. There'll be unprecedented value to people and society as we mature these methods over time. I'm sure these technologies will be viewed, this slide deck will be viewed 30 years from now as like a Franklin stove technology. I was trying to get coal into a stove. And the theme that I like to point out is that we start with principles and curiosity. We build applications both in mission critical and in playful ways. And often we end up with new principles, typically as we try to take our current methods and we face the constraints and and needs of the real world. So I'll stop there.